Up to the last video, we have seen the methods to find two linearly independent solutions of second order linear homogeneous equation. So, when you cannot find even one solution, so how do you find the solutions when I have equation? So, linear equation with variable coefficients when you are given, how do you find these two linearly independent solutions? And all the methods that I have given do not work, and you cannot even find one solution. If you know one solution, you can find the other, or you know how to find some of the ways so you can find both the solutions. When nothing works, how do you find in general? Okay, so let's I'll give you some power series method in this video. I'll introduce you to the power series. So the motivation behind a power series method and how we work out the method. So I'll give you the details. Let's start with the general linear second order homogeneous equation. So that is a naught of x y double dash plus a1 x y dash plus a2 x y equal to 0. So this is the general equation. Okay. So I cannot write the definition because I don't define the domain, because you don't know what exactly my a naught of x. If a naught of x is never be 0 at any place, I can simply divide, then the equation is defined for every x. Okay. So if a naught of x equal to 0 at some x equal to x naught, then x naught is an ordinary point. Okay. If this is 0, if this is non-zero, okay, so all those points at which this is non-zero, they are ordinary points. If a naught of x equal to 0 at x equal to x naught, then x naught is said to be is a singular point. So those values of a naught, those values of x naught at which a naught of x naught is 0, those are singular points. At that point, equation is not defined. Okay. So a set of all for every x for which belongs to, so R you just write belongs to I, containing I is part of R, and I is an interval with ordinary points. So this is what is that. Okay. So you always have a domain that is with ordinary points. So you don't the domain should not have a singular points. Okay. So these are singular points. So we'll start with this. What we do is, when you cannot find any solution, not even a single solution y1, okay, you don't know. So to find two linearly independent solutions, so what we do is we use the method called power series method. Power series. So that means you look for solutions yx in the power series form, some odd constants and n is from 0 to infinity. So you look for solution in this form. Look for yx in this form. Why is it working? So if you simply substitute to the equation, get this constant, then that is the solution. Okay. So we will see how we work out this with this power series method. Before I do this, what is the power series? Power series, general power series. I'll give you the general power series. This is called the power series, n is from 0 to infinity. Some constant Cn, x minus x naught power n is called the power series. Is a power series around x equal to x naught. Okay. So this is the definition of the power series. Any power series is this. So you can clearly see that these are all powers of x minus x naught, because that is what is around x equal to x naught. So what we have is this is the power series around x equal to 0, this one. Okay. So with this definition, so this is actually, you look for a power series solution around 0. Okay. If 0 is part of the domain, that is ordinary point, then we look for power series in this form. So, in general, so what this is the power series, and clearly this power series is finite at x equal to x naught. Okay. So, at x equal to x naught, this power series is actually value of this is clearly C n x minus x power n equal to C 0, so which is finite. So, it converges, that means it converges at x equal to x naught. So, there are three possibilities. It is so this means it is either it is certainly it is a power series always converges at x equal to x naught, and if I know that if sigma n is from 0 to infinity C n x minus x naught power n, this converges at x equal to say some c, then the power series converges C n x minus x naught power n converges for every x mod less than c. Okay. So, that means if you know that a priori that it is power series is finite, just simply substitute x equal to c, and then what you have is if your x naught is here, so this one, so you should say x minus x naught for all the neighborhood of c. This is what happens. Okay. The neighborhood of, so from this up to c, because you know that at x naught it is converging, and you know that it is given that it is at c it is converging. So, you have x, this should be x naught plus c. So, at c means x naught plus c, let us say. Okay. Converges at x equal to x naught plus c, then converges for mod x minus x naught less than c for all x within this interval. So, if this is x naught plus c, given that this is finite here, so I know that x naught minus c up to within this power series converges absolutely. Okay. So, we will see how this, so this property we can easily see. So, if we know that a priori that this is converging x equal to x naught plus c, that means given that it is C n and this constant c power n is from 0 to infinity, this is finite. Okay. Given, this is given, because this series is this is a series, simply series of numbers, this series is converging, number series is converging implies you have nth term is, then this limit is necessary that c power n into C n as n goes to infinity is 0. That means this sequence C n c power n is bounded. Okay. So, C n c power n, this is always some bounded with some m. This is true for every n. Okay. So, now you look at this C n x minus x naught power n is from 0 to infinity. So, this I can rewrite, n is from 0 to infinity, C n x minus x naught I can replace with C n. Okay. So, when you are replacing x by x naught plus c, then you get c, right. So, in the place of x you put x naught plus c, so that becomes c power n. Okay. Divide by or you simply write x minus x naught power n divide by c power n into c power n. Okay. So, this I can do. So, this is equal to n is from 0 to infinity C n c power n, you can write this, and x minus x naught power by c power n, and you know that this is bounded. So, this is less than or equal to sigma n is from 0 to infinity, this is bounded, this is bounded. So, you have this x minus x naught by c power n. If x is here, x minus x naught divided by c is always less than 1. You can easily see that. Okay. So, x is here, x minus x naught minus c is this distance. So, this distance is always bigger than, this is smaller than c. So, it is always less than 1. So, because this is a geometric series is less than 1, geometric series is always finite. So, this implies this is finite. This is true for every x within less than c, x such that x minus x naught is less than. This is how you show that if you know that the power series is converging at x naught plus c, and within this interval it is converging. So, if you want straightforward, you can put you can work with x without x naught. Okay, then it's, if you consider power series around point 0, and you know that it is if you are given that power series is finite at some point c, then minus c to c, the given power series will be converging absolutely. Okay, so you can easily see that. So, because why is it absolute? Absolute also you can work with, because you can just simply take the absolute value and there is no harm. So, when you take the absolute value, this is the absolute values. So, this is still finite. Okay. So, that way is, then if you take the modulus values, when in the power series, when you take the modulus values, if this is finite, then you say that is absolute convergence. Okay. If it is directly, it is converging. If this is converging, then it is, you say that power series is convergence, usual convergence. You take the each of these terms are with modulus, then you say that it is a power series converging absolutely, converges absolutely in the interval x naught, what is the interval, x naught minus c to x naught plus c. Within this interval it is true. So, power series has certain properties. So, you see, by looking at the power series, all these terms are continuous functions. So, if this series is, if you know that a priori that this power series convergence of the power series is uniform, that means you should know what is the uniform convergence. So, converging a series means convergence of a series, some f n of x, n is from 0 to infinity. So, this means this converges means converges, what is the actual meaning of convergence of a series is actually equivalent to put it partial sums you consider. So, these are your sequence, n is from 0 to big N f n of x. So, you consider this. Now, for each n is from 1 to infinity as a sequence, this sequence converges, that is the meaning of this. Okay. So, both are same. So, if these are continuous functions, if this convergence is uniform, then the series or the limit of this sequence is convergent. What is the limit of this sequence partial sums? Is nothing but this finite sum, this infinite sum. Okay. So, if the power series, if sigma f n of x, n is from 0 to infinity, converges uniformly. What is the meaning of uniform convergence? I will just demonstrate with some example. So, example is a simple example I take, x by n. These are functions. So, let us consider f n of x as x by n, f n of x as x by n. Okay, so let me call some g n of x. So, let me see what is if we plot it on a real line. So, let us take x square by n. X square by n equal to 1 if you take is simple x square. Okay, x square. So, half of this if you do, it will come down and it will be expanding. Okay, and as you increase your n, it is going to come down, right. This is how it goes. So, you fix your x value, let us say 0. At 0 this converges to 0. So, g n of 0 converges to 0 as n goes to infinity. This is a calculus at 0. Now, if you consider a point x instead of x away, let us say at some big value, say some 100, a convergence, this convergence is very fast, because you know that it is simply 0 sequence, 0 sequence converges to 0 very fast. But if I consider 100, that means somewhere here. Okay, for x square 100 is here initially, n equal to 1, n equal to 2 it comes here, comes down here. Okay, and for like that you eventually reach. So, the convergence is slow. Okay. So, here is the fastest at 0, and as at x equal to some big number, okay, let us take some big number m. Okay. At m, this convergence is slow. So, if I take it infinity, it is really very big number. So, convergence is slower, it becomes slower and slower. Okay. And how slower it is? So, if they you see it is a fastest, that means fastest and the slow speed is slow, convergence speed is slower and slower. So, its convergence speed is, let us say, so very slow, 0, it means it is very close to 0. Faster means convergence is very fast, okay. The speed is very high, okay. Speed, I am just talking about the speed of convergence. So, slow means speed is very small, and convergence very fast means speed is very high. So, by looking at all these speed, if the speed may be close to 0, but never be 0, right, because you know that fix any x, this converges to 0. Fix any x, gn of x always converges, okay, converges to 0 as n goes to infinity for fix x, fix any x, this is what is true. But the rate of convergence, the speed of convergence is just varying, it depends on x, okay. It is close to 0, so that is in this, and then some finite number, okay. Let us say at 0 is a fast convergence, speed must be, let us put some highest, okay, let us put infinity, so very fast, okay. And so in this, let us say some very fast, some big number, okay, so say 1000, and you see that speed is very small and the infimum value is 0. If the infimum value is 0, provided if you consider all the points of x on the x axis. If you consider all x in the real line, clearly you will see that the infimum of the speeds are 0, it becoming 0. So, that means when you have this so that means it is not uniformly converging. So, if you can say that this convergence, slow convergence, the speed of convergence, if it is if you can curb it, if the slower is you have a bound, lower bound, if you can say that you have some fixed number, then your sequence, this gn of x, converging uniformly as n goes to infinity. So, that means it works for all x. So, if I take some fixed interval, say minus c to c is some number, then I know that at some if I consider it minus c and plus c, the convergence is slower, but it is a fixed number, so it cannot be 0, some number, okay, some fixed number. So, convergence is uniform. This is roughly what is the uniform convergence. Otherwise, it is called pointwise. If you fix x, this convergence, this is a pointwise convergence, okay. And whenever you have this rate of convergence, the speed of convergence, when you have a lower limit, which is a constant number, never be 0, the infimum value of these speeds is 0. If it is 0, it is not uniform convergence, okay. If you have some fixed number which is non-zero, then the speed that means you have the given sequence is uniformly convergent. So, the same thing is true here. So, this convergence uniformly, you know that this converges uniformly, basically this convergence works for all x, okay. Mathematical definition is any convergence is, this convergence means there exists some big number n that depends both the value of x and epsilon. You fix your x, okay, then I get this number such that some big number such that this series n equal to 0 to some big number. So, beyond that big number, okay, to infinity f n of x, this value is actually this you can make it very small, epsilon for epsilon, given epsilon, for any epsilon positive. You give an epsilon positive, I can always make this for which there is some n. This number n depending on both on x, whatever you want to achieve, this epsilon and the value x. If such an n, if it is there that works for all x, then you say that this series is converging uniformly, okay. That is another way of saying, if you look at this, if This is a sequence we are looking at, this is the series we are looking at it. Okay. So, both are same. Series, when you look at it, the functions are here, this is partial sums. Okay. So, partial sums convergence, it will have a infimum. So, you have a non-zero infimum speed of convergence for all values of x. Okay. That means there is a sum n that works for all x, for all x. Okay. So, if it does not depend on x, that works for all that depends only on epsilon, okay, and for every x this is true, then you say that it converges uniform. That is the uniform convergence. Okay. This is the definition of uniform convergence. If this should work for every x, if no, this exists that works, that depends only on x and epsilon, then you say that it is pointwise convergence. Okay. So, this is pointwise convergence. Once I remove this x, this which works for every x, this works for every x, then this pointwise becomes uniform convergence. That is the difference. Okay. So, when you know that your given power series is uniformly convergent, then the power series convergence n is from 0 to infinity. So, now I use this Cn x power n. Okay. So, I am using power series around 0. This is continuous. Okay. This itself become continuous because partial sums, each of them are simply polynomials, they are all continuous functions. Continuous functions converges to a continuous function when it is uniform convergence. Okay. So, if this power series, if this converges uniformly, then the series Cn x power n as a function is continuous. Okay. And again, if this is uniform convergence, then this series, derivative of this series n is from 0 to infinity, Cn x power n is actually converges to some other thing. So, you have Cn constants n into x power n minus 1. So, n equal to 0 means it does not make any sense. So, it should from 1 to infinity. So, if you differentiate term by term, C naught plus C1 x, if you once you differentiate, C naught will go. So, it starts with n is from 1 to infinity. This is a derivative, makes sense, that is simply term by term differentiation, and this converges. Okay. This actually converges uniformly. Again, this also converges uniformly. This series after differentiation is also converging uniformly. So, this is what it means. So, this is exactly we use if this is the case. If you have a convergence of a power series, then the derivative of this is actually this series which converges uniformly. So, you can do, that means you can do the power series, you can differentiate as a term by term differentiation derivative. So, you can simply substitute into the differential equation. In the place of y, if you put this power series, y double dash means you simply replace term by term differentiation you can do. Okay. So, that is the meaning of these are the properties of power series 1 or 2. And you also have some other property, like if it is uniform convergence, you can do the term by term integration also. So, I am just, we can do it, but whenever it is we do not use it, if it is required I will give you later. Okay. With this introduction to the power series, let us start, let us go back to the equation. So, your equation is y double dash plus a1 by a naught of x, let us say you divide it, y dash plus a2x by a naught x, y equal to 0. Okay. And x belongs to I, that contains an R. So, where I is, so set of all x a naught of x not equal to 0 for every x belongs to I. So, that is how I could divide it. If it is not, that is not part of the domain, as I explained earlier. So, wherever this a naught of x is 0, so that point is not part of the domain of the differential equation. Okay. So, assume that your I is let us say some simple interval, okay, 0, around 0, some interval. Okay. So, let us say some interval, let us say minus r to r. Okay. So, if you call this function and all with these functions, okay, you consider these functions, let us call this px, let us call this Qx. If Px has a power series representation, that means you consider this Px. Px is assume that it is continuous differentiable, and so that you can find its Taylor series around the point 0. Okay. Then it will have whatever Taylor series is also a power series for that function Px. Okay. So, if Px has a power series representation, Px Qx has power series representation, and this series and these power series and these series converges in minus R to R. Then we can look for power series solution Yx in terms of Cn. Cn's are unknowns, x power n is from 0 to infinity. So, you can look for power series expansion in the I in this interval. So, you have now you have this equation, you do not know how to find two linearly independent solutions. So, you look at this Px and Qx, they are having power series representations. Okay. They have a power series for P and Q, and they actually converges in minus R to R at every value, okay, for some R positive. Okay. So, this is what you have. So, if you have that, so if I is that, if I is actually minus R to R, then you can look for power series. There exists a power series solution. So, power series also you can look for power series solution for Y. That is a theorem without proof. Okay. It is actually theorem without proof I am giving you. So, once you have this power series, this series, once you get a power series, this you look for solution in this form, get your constants, Cn's are unknowns. Once you substitute this Y into the equation, get your Cn's, then your Yx, which is the power series, after finding this Cn's, Cn x power n, converges for every x in I. Once it is converges at one point in I, means you see, let us say minus R to R. Okay, this is minus R to R. If it converges at one point, means within this it is absolutely convergent. That is what we have seen by earlier. Okay. So, like that every point, so it is there everywhere absolutely convergent. So, it is actually you can say that you close this interval. So, every closed interval you consider in this, you can say that is actually converges uniformly, because the power series is always uniform convergence, you can show that. So, once you have absolute convergence, if you choose on a closed interval, that is also the convergence becomes uniform convergence. Okay. So, that is the advantage. So, that is also from the calculus I am assuming if your power series is converging on a closed interval, then it is actually converging uniformly. So, once you have a uniform convergence, you can just differentiate. Y dash will be derivative of this series, that is nothing but term by term differentiation, that you can substitute and get your Cn's. Okay. So, if you are given an equation, second order linear homogeneous equation, but with variable coefficients, and you divide this coefficient of y double dash, and then what you have is a1 by a naught, a2 by a naught. These functions, if you call them as Px and Qx, if this Px and Qx are having power series representations which have a common convergence area, let us say minus R to R, okay, then you will have a solution, power series solutions, that is the theorem without proof. Okay. So, you can have a power series solution within the same interval minus R to R. So, you can look for power series solutions. So, this I will demonstrate in my next video with an example. Okay.